lecture you today, so I just go through the topics that we have discussed. What we discussed in chapter 5 was mostly about autocorrelation and the relationship between autocorrelation and power spectral density. So before I go through the review, what is the meaning of power spectral density? We went through this at least 5-6 times. What does it tell you? If I have a signal, let's say X, and say power spectral density of this signal is something like this, what does it tell me? What's the meaning of power spectral density?
Is it the average power?
Per
Hertz?
per frequency, yeah. So it tells you signal X, whatever is here, it has maximum power at frequency 0. And it has this much power at this particular frequency, and so on. And it has no power at frequency above this. So it's a band-limited signal. That's what it tells you. So the unit here should be watts per hertz, because it's average power per unit hertz. So if I want to get the average power of the signal, what do I do? You're getting there, you're getting there. This graph shows how much power I have per frequency.
Area?
Yes, the area. So the average power would be this area. So that means I have to integrate power spectral density from minus infinity to plus infinity. In this case, I really don't have to go to minus infinity. I look at this. If it is minus b plus b, so I go from minus b to plus b. So you have to understand, this is a very simple concept. Now, let me ask you this. If you have a signal that power spectral density is like this, what does it tell you? My signal X has power spectral density, which is just a delta function at frequency 0. What does it mean?
DC.
It's just DC signal. It's just DC signal. And it depends what's the weight of this delta function. If it is 1, it means it has 1 watts at 0 frequency. So when you integrate a delta function, you already know this. In this case, again, you don't have to go from minus infinity to plus infinity. You can go from 0 minus to 0 plus. I don't know how you learned this, but different books, they have different way of showing this. 0 minus to 0 plus, because it's really 0 everywhere except at 0. And this integral would be equal to 1. So the DC power is 1 watt. Okay, now, if I have a power spectral density which looks like this, what does it tell me? The signal is a pure sinusoid, right, at frequency of 100 hertz. And the average power in that sinusoid is 2 watts. So you learn that. So I might have signals that have different components. The power spectral density is not just one function. You might have signals with power spectral density something like this. Choppy, like this. So again, this is just a characteristic of the signal in frequency domain. It has no energy between these two frequencies, it has energy between these two frequencies, and so on. So if I want the average power in this signal, again, I have to look at the area under this. Or I can have a signal with this kind of power spectral density. What does it tell me? It tells me signal has energies from frequency minus B to plus B. Signal also has a DC component. Again, if I want to find the total power, I would get the average power here. Under this, it will give me the average AC power. So if I ask you what is the average AC power in this signal, all you have to do is get the area under this part. What is the average DC power? You look at this guy, let's say it is 2, weight is 2, so the average DC power would be 2 watts. So, any question on these things? It's very straightforward. Power spectral density. Actually, we covered this in previous chapters. In chapter 5, we also discussed autocorrelation. What was relationship between autocorrelation and power spectral density? Autocorrelation of signal X was shown this way. So there is a relationship which is usually for random processes. And I told you before why we go through autocorrelation of random processes, because it's not like known signals. In known signals, usually to get the average power, you look at the Fourier transform. Well, today is out, but we don't have any more classes. But for exam, if you are late more than 10 minutes, I will not let you in. That's the rule. If you are late more than 10 minutes, I will not let you in. So I let you. Okay. Because it's very, very disturbing when you come late, especially when the door is open and it's not right. So, lost my thought. Autocorrelation has a relationship with power spectral density. And the relationship was autocorrelation was inverse Fourier transform of power spectral density. And every time we talk about inverse Fourier transform, we usually have a signal in time domain, but this is tau domain. That's the designation we use. So here we put t equal to tau. Means you can use the table in your book or whatever you have, except when you get inverse Fourier transform, you use tau instead of t. So if let's say a signal has this power spectral density, what is autocorrelation? Flat. 1. Because inverse Fourier transform of delta f is 1. And if the weight here is x, whatever it is, k, then it would be k. If I have a signal with with this kind of power spectral density, delta function at F1, delta function at F2, and the weight of each one is half, what would be autocorrelation?
Sinusoids.
Sine, yes. It would be cosine of
2 pi
2 pi, correct?
F1 tau.
Very simple, right? Very simple. I cannot make it simpler than this. If I have a signal with this as autocorrelation, it's a random process, and this is the autocorrelation. What would be power spectral density? Sinc, exactly. You have to get inverse Fourier transform of this, which gives us what? T over 2b. You can look at the table and find out what you have. So it would be sinc function. What else? Any question on any of these? So, for chapter 5, what you need to learn is we have a random process. What is a random process? And random process comes with autocorrelation, how to calculate autocorrelation. And sometimes you don't have to calculate autocorrelation. Autocorrelation can be given in a graph form. And then you are asked to calculate whatever. AC power, DC power, and so on. If my autocorrelation is like this, what does it tell you?
It's an impulse in the frequency. I mean,
Power spectral density, again, is an impulse at F equal to 0. So it is a DC and whatever. So it's really, what we're talking about is back to chapter 2, is Fourier transform and inverse Fourier transform. So how to convert autocorrelation to power spectral density and how to get autocorrelation from power spectral density. And why do we do all of this? These are usually done for random processes. In random process, it's not like what you learned in previous courses. You were dealing with known signals like sinusoid or rectangular. It was very easy to calculate the average power. But when you have a random signal, it is not that easy to calculate the average power. So the best way to do is to get the signal, either get the autocorrelation of the signal, and then convert autocorrelation to power spectral density. Then you can analyze your signal and anything you want. So, let's say you also get from autocorrelation, you also, after you learn let's say you already given autocorrelation, and from autocorrelation you get power spectral density. If I ask you what is Nyquist rate, that's in your book, what is Nyquist rate?
Is it the minimum?
I'm asking you.
Oh, okay.
I want an answer, not a question.
Okay.
What is Nyquist rate for this signal? You guys haven't studied.
Twice the frequency?
Twice
The minimum.
twice as the bandwidth in this case. It's the way it's defined.
They asked me that question at an interview.
Really?
Yeah.
Okay, good. You know, in this chapter, you have to look at it as just defined this way because we haven't got to the digital communication, we haven't got to the sampling frequency and so on. So in this chapter, just define Nyquist rate, they say it's defined this way. What is Nyquist interval for this signal? Nyquist interval is equal to 1 over 2b, correct. It is 1 over Nyquist rate. You have to be familiar with these terminologies. If you know it, then the question is so simple. Any questions so far? Let's say you have this signal. What is Nyquist rate again? 2b. Now let's say you have a signal with this kind of power spectral density. What would be Nyquist rate? 2A? Just trying to test it. Because overall power spectral density would be this guy plus this guy, right? And when you add them up, it looks like something like this. So, what would be, let's say this is the signal you have in time domain, or let's call it x of t. And I ask you to find the Nyquist rate for this signal. That's fine, but how do you get it? That's the question. You're a little bit too fast.
But you need to find the frequency, right?
What?
But you need to find the frequency.
You need to find the frequency. In this case, since it's a known signal,
Would it be 200?
you don't have to go through autocorrelation. So some of you learn something and you stick with it. You don't want to get away. I'm just testing you here because I wanted to know if somebody's really say, well, we have to find autocorrelation. No. You have to find the signal in the frequency domain. The signal in the frequency domain would be a gate function, right? So if you look at it, it is something like this. The Nyquist would be 2 times 100, which is 200. What would be the Nyquist rate of this guy? How do you get this one?
Would it be, well,
I give you a hint. This can be written as sinc of 200t times 300. It's like an auction.